Hello again. Tonight's going to be a short one. I had lots of things to do this week, various personal appointment things, and Hurricane Milton decided to come through. No significant damage to where I am, or I check with our local folks here, and everybody seems to suffer the wind and rain. We're on the southeast coast of Florida, so didn't directly hit us. But anyway, tonight we're going to talk about the expansion of the universe and how it was a constant. And now they're like, maybe not a constant, maybe a variable. But I think ultimately, given the different values and observations, that they need to think of it as a little more of a parameter and a formula where you can have multiple uh, variables associated with it. And I think that'll fix the problem, get all the ducks lined up properly. So as I said, I spent lots of stuff this week, watched videos in between, and from what I can tell about them trying to figure out the expansion or acceleration of the universe, they're close. They've got one more dot to connect, and that's what we'll talk about. So it all comes down to the math, specifically in this case, algebraic formulas. Don't worry, it won't be that deep. Maybe a solid toe dipping in the aspects of math. I won't present you with any formulas and notation, and no graphs with value uncertainty range bars, the stuff you might see in some of the videos that I point to at the end. In a mathematical formula, a factor, something that changes the end result value, can be a constant, it can be a variable, or it can be parametric or parameter, which can be its own formula, sometimes referred to as a factor, but there's multiple or multivariate parameters. With more observations, there have been more refined statements regarding the acceleration of the expansion of the universe. Early on, the universe was considered static, steady state, not expanding. And then they started making more observations and realizing that things are changing over time. The universe is expanding, typically by what we would think of as red shifting as things are further away. And they're looking at the same brightness lights, the standard candles, so to speak. Now, we're not going to talk about why it's expanding, be it lambda cold dark matter, dark energy, modified Newtonian dynamics, or any of that stuff. We'll leave that for other people to discuss. Just remember that the expansion rate was initially considered a constant, and this was referred to as the Hubble constant. A constant is an unchanging value. With additional observations, the results are not accepted by all, but let's say by most. They realized that the constant acceleration should no longer be considered a constant acceleration, but a variable. So it changes. It's an acceleration that changes over time. In aerodynamics, an acceleration that changes over time sometimes is referred to as jerk. And I know this because I played with very small drones, and the diameter between the various propeller units on small drones gives it a very tight jerk, so we can do in-place vertical and horizontal flips because of this parameter called jerk. It's not only you're accelerating, but you're increasing the acceleration. The universe has a jerk. The initial observations were from different kinds of observatories, both on the ground and in space. Observatories on the ground started using lasers to simulate stars, to subtract out the distortion of the atmosphere so they could get more precise positioning on stars. Then there were things put out into space to observe in the cosmic microwave background. First COBE and then Planck. And they increased the resolution between COBE and Planck. So now you can see smaller objects, and you can, through spectral analysis, determine their shift. And we've now got the James Webb Space Telescope, and more recently, not just that it can observe better in infrared at higher resolution and it's really dark out at Lagrange point 2, but also they're starting to use gravitational lensing so they can get different views of the same stars and see how the dilation due to gravity changes affects the observed brightness of stars. And recently they did that for a supernova in another galaxy. So now they have a better candle, a more accurate range candle. And so the difference in the expansion of the universe between microwave background and JWST gravitational lensed imaging, which is closer to infrared, near infrared actually, they've moved apart a little bit. They're no longer close enough to be considered just a fudge. They're now far enough apart that, okay, we've got a problem here, folks. And this is where you'll hear things like the crisis in cosmology or Hubble tension. And what they're referring to is this particular number that through all these different types, different wavelengths of observations, they come away with different numbers. And the numbers range from 67.4 to 73.24 kilometers per second per megaparsec. That's a million parsecs. And a parsec is 3.26 light years. And a light year is about 6 trillion miles. They just multiply it all up and you'll find that the difference between 67 and 73 may not sound like much, but when you express it out as kilometers per second per megaparsec, it's a noteworthy value. It's not it's not trivial. It's something that science wants to get closer agreement on. But they also, and in their observations, have a plus or minus accuracy factor. So it's not just that it's like 67.4 and 73.24. Each of those observations have range bars associated with them. And they'd like to get not only the numbers closer together, but the range bars tighter. So I said, well, I'm not a mathematician by profession or degree, but I do know computer science and parameters and formulas and such. So in general, most agree that the Hubble value is not a constant. That's an excellent first step to getting it right. But now they're saying it's a variable, but they're seeing a different value for that variable if it's microwave, like cosmic microwave background, versus visual optical versus infrared. And they're still far enough apart that somebody needs to find a way to resolve this. I don't think going from a constant to a variable is sufficient. I think they need to take one more step to say it's a multivariate parameter. So instead of it being a number or like a letter for a formula for a variable, it needs to be, a parentheses expression with a couple of parameters in it. One of which would be a constant. That's, the baseline. All the expansion can show at least this much expansion. So that's the baseline. That's the constant. Maybe that's just a modified version of the Hubble constant. Then you need to say, well, at the beginning, at the Big Bang, the acceleration was this, but now we're seeing over time, the acceleration is increasing. So you have a parameter there that says time increases the acceleration of the expansion. And since we have a difference between microwaves, infrared, and visible, I think there needs to be a parameter in there for what wavelength are you observing in? And I think if you do all three of those things instead of a simple constant or a variable, I think now you have a chance of saying, we've got a formula that can now squeeze everything together and you can get whatever number you get out of it based upon that formula. Go from a constant to a variable to a factor that has multiple parameters in it. And I think you can figure this out. But I'm not going to do that part. I'll leave that up to the professionals. As we observe things, as observations have improved, as the instruments have improved, we get things tighter. It's not fuzzy anymore. It's more specific values. But we've also seen that as you look out into the universe, things are shifted in wavelength. Things that might be visible are towards the red, or things that are red are towards infrared, or things that are infrared are towards microwave. And to me, that's a progression. And as the universe grows bigger, I don't see any reason why it can't go from microwaves down into longer radio wavelengths. And we've also noticed that if you look at some of the earlier observations and some of the most recent observations in the same wavelength, that it's also stretched, which says there's an acceleration of the acceleration based upon time. So time should be a parameter. The end result is you have a baseline constant and you have time and wavelength as parameters, and then that becomes an additional factor in the formula. I said it was going to be short. So in conclusion, there are numerical disagreements in the observations from multiple sources. Instruments and recording mediums, you can go from basically eyeballs to film to digital recording to improved sensors. All of that's been narrowing down the observations to get more of a pinpoint location on things. And we've improved the processing techniques. We won't go for 2 sigma anymore. 5 sigma is kind of like where respect starts to come in. And 6 sigma is like, yeah, we got it now. We have a variety of observing locations. Sure, you can be on the ground in an observatory up in a mountain, or you can be in Earth orbit like Hubble, or you can be out at L2 like James Webb Space Telescope. And then the conditions at altitude or on the ground can be affected by weather. And so you have to use lasers bouncing off of the underside of the atmosphere to get rid of the distortion. So now you can have highly accurate processes for all of your observations. And since you now have those narrowed items and you have different camps, like we're microwave, we're visible, we're infrared. Microwave is separate from visible and infrared and visible are close, but not exactly the same. So resolve the crisis, eliminate the tension, bump it up from a constant to algebra. And I think you're going to find that, I think that'll solve the problem. And then you'll have things that, well, based upon this being a radio telescope, we need to factor it this way. Based upon this being infrared or visible or even UV or X-ray or gamma, you can factor in the wavelength of the photons you're observing. But that's just my opinion. I think they ought to give it a try. When I publish this publicly, maybe somebody will see it and go, let me think about that. And then 2 of my favorites on YouTube is Anton Petrov and PBS Space Time. So those are in the PDF that I sent out earlier. And then if you're unfamiliar with the Hubble tension or the crisis in cosmology, there's an article there for that. And if you don't know what a parsec is, definition of a parsec.
Thank you.
It's the parallax of 1 arc second.
I wondered what that meant. Okay.
Yeah, so that's where you get parsec from. It's the parallax of 1 arc second. Think of it as the Earth is going around the sun. And if we go and look at a star from this side of the orbit, and we see the star is there, and then, half a year later, we're over at this side of the orbit, and we look at the same star, it's not going to be in the same part of the sky. And if you go, well, how does that work? I will give you a personal example. Hold your finger out in front of your nose. Cover one eye. Switch and cover the other eye. Your finger moves. No, don't move your finger. Just keep your finger out in front of, close one eye, and then close that eye and open the other eye. And the finger will move slightly. That's parallax.
Yeah. The background changes too.
Yes. Yeah. So that's what parallax of 1 arc second is the parallax over the width of the orbit of the Earth around the sun. So now you can see
it's based on something believable. Yeah. Okay.
And then some controversial topics, the size of the observable universe and the age of the universe. It just keeps getting bigger and older. One of the factors that I think they took into account most recently is if you judge the redshift and you say, well, obviously that's how far away that distant star is by its redshift. Okay, but in the time it took for that light to go from that star to your observatory, that star has moved out further by a significant amount. So when you think, well, the universe is, 13.6 billion light years across. Well, not exactly, you know, more than double that, because the light that was there came here over a period of time, 13.6 billion years. And in that time, it's moved out farther over 13.6 billion years. And we know the universe is expanding at an accelerated rate. So it's moving away even farther, faster. So, yeah. But it's gone beyond the point where we're seeing its light anymore. It's now accelerating close enough to the speed of light that we may, at some point, never see light from it anymore, because all the close light has come by. And now it's moving away far enough that that light will take even longer to get to us. So, size of the universe. And with that, age. So, yeah. Okay, I thought that would be an interesting short topic. We'll see if a short topic on a deep subject without any math or graphs draws people's attention once I put it out there publicly. So how many people were aware of the Hubble constant?
Yep.
The expansion of the universe. Okay. How many people knew that it was maybe not a constant, maybe a variable that changes over time?
Yeah. Very confusing.
Yep. That's the tension. That's the crisis. And it's really between two camps, the microwave radio astronomers and the infrared astronomers, and the legacy optical stuff from like Hubble Space Telescope, that is. The numbers are too wide apart. Can't have that. That makes mathematicians' brain itchy.
And so you're going to be more appreciated by which camp?
Hopefully, if the use of it as a multivariate parameter works, then there should be a coming together of both camps, because both their numbers can be right. I know, socially speaking, whenever there's an answer and another answer, and this forms two different competing groups, everybody wants to see who's right and who's wrong. Well, this would actually say, you're both right. It's just not one number. It's a formula. And I'm sure some will not be impressed by the fact that the other guy didn't lose.
Right. And I'm just thinking,
are both camps studying the same region of space? Because apparently the expansion is slightly different in different areas.
Yes, it is. And if you watch the latest stuff, it is different in different areas, which means the expansion of the universe is not smooth. It's not uniform in all directions. It's lumpy. Yeah, the different camps are looking at different objects in different wavelengths. For example, the microwave background has improved in resolution as a result of the Planck satellite, but it's nowhere near as accurate in positioning as the James Webb Space Telescope, because it works in infrared, which is nowhere as accurate in positioning of brighter things as the Hubble Space Telescope, because it can look in ultraviolet. So, less fuzzy objects. It's a numbers game out there. Okay. Comments or questions on tonight's presentation before I stop recording? Okay.